Welcome to hands-on CPU session. So what we will try in this part. First of all, we will look at implementation for some laminar plane flow test case, and we will work with uniform grid. Then we will try to change boundary conditions and try to use first generated geometry and then geometry from STL file. So, and for this purpose we need a STL file, so please use this link, this both link to the same data. It's here is only shorter. Yeah, this was I created short link, too easy to type, and download this data. Yeah, we need this later. So then, okay. Then we look first in the code. I hope everybody has working copy of VirtualFluids on his computer. Yeah. So and okay, I close some files, and we looking in apps. Yeah, here folder apps, and we have here laminar plane flow app. So laminar plane flow CPP. So I hope the font is okay, as font size is okay. Can you see this? So okay. Yeah, there's a full last line. Okay, and we start first with main. Also here main function. I think I see some similar in Henry code. It was we use this try catch construction to catch some exceptions. Yeah, and because what I saw in Martin's example, it was some if construction to catch if exists this parameter or not in config file. Yeah, if you use simple this try catch, you don't need this to do because if you don't have this parameter or something wrong, you have an exception in your program. Yeah, the program will be not work if you, for example, have some parameter which not exist in config file. Then you have exception. Yeah, stop it. Simple. Yeah, and we use the same config file. Yeah, config file configuration class. This class for config file, and the syntax is the same. Yeah, but it's for your notice. Yeah, you don't need always ask if you have this parameter or not. Yeah, simple use this try and catch construction. So and yeah, it's implemented here in main. You see we get information from a command line is actually it is your configuration file with path. Yeah, and gives this in load config this function, this static function simple, which create for us this config object, config file object, configuration object. Yeah. So and then we call here simple run function which actually implements this test case. Yeah, and you can see here's run function, and run function has parameter this configuration file config. Yeah, we as parameter we give for run this configuration file. Then we can use this for reading different parameters. So what we need to include, actually we need opposite to not opposite, yeah, together with some maybe standard C++ include files, we need to include this VirtualFluids.h file. Yeah, and in this file we can look in this. Yeah, actually are all passes to all classes in the VirtualFluid CPU submodule. Yeah, you don't need to make special includes. Yeah, you include simple this VirtualFluids.h file, and then you have automatically access to all classes in this library. Okay. So then yeah, of course, not forget also if you write, for example, new application, yeah, not forget this header, include this header, because otherwise you don't yeah, your pipeline will be not successful. So okay, then first we look in the run function. Yeah, first it's the same. Yeah, you see it's the same like in GPU code. We can read some parameters. So, and I think Hussein explained yesterday, yeah, which different parameters in config file. Actually, in config file we need also actually we need to successful pipeline, we need add these two lines. But of course in CPP good to have this complete header. In config file it's enough these 2 lines in principle. Yeah. So yeah, I can repeat again what we have this in config file is passed to the output directory, number of threads. Yeah, we can decide how many threads we can use for this simulation. For example, I have only 4 cores in my laptop. I can use only 4 threads. I can set, of course, more threads, but doesn't make any sense. So then we have this block in X. It means how many nodes we have in the block, as the block size in nodes. Bounding box is, it means how many nodes we have in our grid. Yeah, size of the grid in terms of nodes. And yeah, delta X is grid spacing. So, and yeah, and you can see this refined level, and here we can set how many levels we want to have in our refinement. But we want to first start with uniform grid, and in this case we should set refined level to 0. Okay, please set refined level to 0, and because about refinement we will talk in second hands-on. And this part, new starts, restart step, we will also speak in second part. Yeah, this also. And what's interesting for us is output time and end time parameters. So output time, it means it's set which time step we want to have output, in this case 1000, and end time until up to how many time steps we want to simulate. Simple, yeah. Okay. So yeah.
In the configuration file, there is this local NX and bounding box. So they are like couples. So we have to discretize the bounding box in, let's say, I mean, not in a fraction. I mean, if we divided any number in the bounding box, for example, the first one, with the first one in the block nx, we should get an integer, because this is only one choice. This one can choose in order to divide the bounding box into blocks.
Yeah, we can control here with these two parameters how many blocks we have in our block grid. Yeah, so with two parameters. Yeah, because and we need, of course, choose the parameters. Yeah, proportional. Yeah, this we have some integer number of number of blocks, yeah, in the grid. So but I will show you how, if we change this, how is influence our block grid. Okay, but I return to this main to the run function. Okay, and in this line we need always, yeah, input this line. As I said, yeah, with default we use always MPI. Yeah, we decided, okay, this was design decision, that's because software actually was optimized and developed for some parallel running, yeah, for with MPI or with OpenMP, but this default we have this MPI yeah, we can use this MPI communication. Yeah, we can set, and we decided, okay, this in most of cases, yeah, we will use MPI. Yeah, because it's don't like GPU, which you can have in your laptop or your workstation, some powerful GPU, and compute some simulation which makes sense. Yeah, not so simple example. Yeah, I mean, with CPU is not so easy. Yeah, and typical, if you do some real simulation, some serious project, then you need a cluster actually, and more computer power, and then you will always use MPI. So maybe in the future we have more powerful CPUs. Who knows? But at the moment it's so. Okay, and yeah, this part is always, you will see in if you open other applications, yeah, you will see always this part, typical, yeah, open config file, or read some parameters from config file, and define this MPI communicator. Yeah, but again, it's actually universal. I mean, what you can see, you have this generalized class communicator, and you can, of course, implement your own communicator for other communication framework. Yeah, not special MPI. At the moment, is only MPI implemented here, or communicator for MPI. But if you have more, for your purpose, more better communication framework, you can always implement new communicator and new transmitter and use other communication framework. So, and it's independent of this latest voicemail logic and boundary condition, nothing. Yeah, that's totally independent. So then you can easily port to other hardware. So, and okay, then here we have some okay, variables, and yeah, for setting up our parameters, as which means as a laminar plane flow, that we have two walls, yeah, and periodical boundary condition in the other direction, and yeah, pressure in inflow, outflow. So, and yeah, okay, and this other thing which we need always define, but if you use this or not, it's depend of case. In this case, we define it because it's a parameter always use it for the simulation, but it can be simply yeah, empty object. Yeah, we can say. So you create this, but you don't set it up. What is it actually? It's LBM unit converter. It means if you want to in default, you use latest Boltzmann units. Yeah, if you don't set up this latest unit LBM unit converter, you have latest units. If you need to conduct your simulation, if you want to use CI, for example, units, yeah, or other units, and then you need to use this unit converter. Yeah, then in these cases does nothing this converter. Yeah, because we don't set up this relationship between latest units and other units. Yeah, but you can we can look in this converter. So there is some predefined cases. Yeah, you can for CI units, for water, seawater, air, so normal air 20 degrees Celsius, and oil. Yeah, this is some. You can simply use this. Yeah, this, or you can define your own. Yeah, converter units. This one. So, and so you see there is some list of function. Yeah, and simple. Then, so if you want to convert something, you call this function get factor viscosity, for example, LB to word, yeah, LB to W, and yeah, multiply with your, for example, LBM unit, yeah, and this produce for this convert in word unit. So yeah. This totally your decision how you want to do this. Yeah, for example, for this, but because very often some academical benchmarks, yeah, this dimensionless, yeah, this don't have any units, and we you can decide, okay, I want to work with SI units or other units or simple in LBM units, and then I produce some comparison and dimension loss less, yeah. it's totally your decision. But I want to show you, yeah, there is this possibility to apply SI units or other units, yeah, you can, it's in principle it's universal, yeah, because what you said here, yeah, okay, the output, you can apply this function to string to the object of this class, and this produce you output, yeah, this of course in SI units, yeah, because it's general. So, but theoretical, you can use any units what you want, yeah, not all, not special metrics. So you want to this is in principle those scale class, yeah, where scale between one LBM units and other units what you need, okay.
Could this affect also the results in power view? If I want to represent them in SI units, this could also be used like this.
Yes, I show you. I show you later. Yeah. So if you don't set, yeah, again, how you can set something here. So here is main constructor. As you see, it's different constructors, and some as a special for this predefined values, and this is general constructor, and this not other. You set here your reference length in your word units, yeah, that's for example SI units. Speed of sound is in SI units, or your word units, and density, and then a reference unit in lattice units, speed of sound as a default. This is default value, but you can change this. You can set your own, yeah, value with some, yeah. It's sometimes we need to set some artificial speed of sound, yeah, to avoid instability, for example, or something like this, yeah. And last parameter, again, yeah, and density in lattice units also default is 1, yeah, we have 1. So, but it can be also and in principle you set here this relationship, yeah, between two, and a class provides you functionality to scale. Yeah, you can do this manually, but class is here and is used for output, and for, yeah, it's actually general for output, yeah. Then you can produce your data in lattice units or in other units on SI. In this case, for example, SI units, yeah. So, and then this was a question, yeah. So if I can have this in power view, of course, if you apply your scale factors with this converter, yeah, for the output, then you have in SI units, for example, yeah. But you can configure this converter also for non-metric, for example, units or something like this, yeah, doesn't matter. This only the standard output and this predefined values was implemented for SI units because it's, yeah, standard thing in at least in Europe, I think.
Outside of United States.
Yeah. So okay, but it's pretty nice. So then, okay, here we I want to go through, yeah, the source code first, and yeah, if you have some question, we can then discuss this. As here we define the bounding box and for our grid, yeah. If you generate some grid, as always, we defined we can say maximum hole bounding box in which we want to have our grid. Yeah, it's not necessary that grid at the end will be also has this form, but yeah, we define a domain where we which size has this simulation domain. So it's some special variable. I call it this block length, but it doesn't matter. It's only to yeah, to some extension for the geometry if you create boundary conditions. Yeah, it's misleading. Maybe we need to choose other name. Yeah. But okay, and here block is boundary conditions. Yeah, here we set these boundary conditions. Okay, at this point I think this started different to the GPU code. Yeah. So and you can see again we have this BC strategy. Yeah, and this BC classes. So then we need as of for in our case we have no slip walls. Or we have some walls and we want to set no slip boundary conditions on this. Then we choose no slip BC. Yeah, we create this new object from class no slip BC, and so we can look in this table again. Yeah, so we have this no slip BC, and then we have choose. Yeah, we can choose thin wall, no slip, and no slip interpolated BC strategy. Yeah, as a thin wall is what I think as Martin explained. Yeah, the case if we have very thin wall between two nodes that we don't have some solid node inside the object or the opposite side of the wall. Yeah, then this only for this case.
I mean, at this point, it may be useful to say that they are also interpolated.
Yes. It's if we have two boundary nodes, yeah, as in between the wall, and we have on both sides boundary nodes.
Yeah, no, because there is no.
You mean yes? Yeah.
The thin wall does not include in their name.
Yes, it's in principle the same. This is the same algorithm, but special case this thin wall case.
But it takes into consideration thin walls. It applies interpolated boundary condition.
Yes.
There is a normal boundary condition, and also takes into account this special case.
Yes. We can say the special implementation for this no slip interpolated boundary condition, but the kind of boundary condition both the same as no slip, but yeah, we can use this table to look for some strategy, which strategy we need in this case. So and so then you can see we create this BC strategy object. This is no slip interpolated. We use class, but as we use always generalized as a pointer to abstract class. Yeah, this idea that we create concrete. This creates this idea of this strategy pattern. Yeah, we create generalized pointer to concrete realization, to concrete implementation of this strategy. Okay, and we set this strategy in this no slip BC, in this BC object. So. And this is your definition of boundary condition in this case, or which boundary we define different boundary conditions. Okay, as at first. So we need three kind of boundary conditions. There's no slip, then we define pressure BC1, object as for pressure on the left side, for example, yeah, and pressure BC2 for right side as the channel. So the syntax is the same, yeah. It's always here that only other BC class, and again we look in this table, yeah, pressure BC, and we can choose between different BC strategies. Yeah? As we have implementation for three strategies. This outflow non-frequent, it means what is outflow without reflection. This is second is outflow without reflection with pressure, with additional pressure.
So now you can ask the question, is this an outflow or a pressure boundary condition?
Yeah.
Actually, I would rather say it's a pressure boundary. It's kind of a pressure boundary condition. Or you could say...
Yeah, it's something combine it.
So the idea behind this is usually you want to end your domain with a... I mean, pretty often you want your domain ended with a pressure. So you said at the outlet we have pressure 0 or something like that. So given pressure. But if you just put there a strict pressure boundary condition because you have not completely incompressible flow, so this will always keep the pressure at this particular value. So when you have a wave, a sound wave coming into this, so this will be returned. Yeah, and this may cause you some problems. So the outflow with no reflection, this is an extrapolation boundary condition that has a specific timing implemented such that pressure waves can easily leave the domain, but then you're just extrapolating the flow and you cannot give any pressure at the outlet. So if you want to have a pressure at the outlet because you simply need a direct wave boundary condition somewhere in your domain, but you don't want to have the reflection, then there is this compromise, which I believe is from Hussein, where this is not completely non-reflective and it's not completely nailing the pressure down. It's like you do something like partly pressure boundary condition and partly non-reflecting, and you combine the two, and then what will happen? You will actually have a small reflection, but the pressure will slowly return to the value that you specify.
Okay. Okay. The next step, okay, is this line. Yeah, it's not necessary that defined here, but it's defined here in this case. I think that's because in the previous version of this test case, yeah, you needed, it was needed to, to use the active use this BC visitor to set some boundary conditions, but I saw this a little bit not conformable, and I re-implemented this refactored to that is completely hide it from the user point of view. What happens then? Which this relationship is visitor, and in actual version you need only define this. Yeah, you need define this and apply this later. Yeah, then it in principle you can define this later before you apply this. But okay, it's here in this source code, it's on this place. Yeah. Yeah, in principle, it's logical also that we in this block define both. Yeah, boundary condition is boundary condition visitor, but it will be used later. Okay, so then here next part is defining of our grid object. Yeah, this class grid 3D, and as parameter we have this communicator. Yeah. And you can see also this general communicator class is maybe any communicator, but in our case we have MPI communicator. And we can set, of course, this periodic boundary, as here also in the grid, as we can say in which direction is periodic, and we say okay, in this z direction should be periodic. Okay. Then is true, parameter true. Then we need to set grid spacing, our delta x, and and dimension for block. Also how many nodes we have in each direction in the block. Yeah, and that which we define here. So yeah, this block in X, yeah, you see the set block in X, and so and yes, and this was a bounding box what we defined here. Yeah, bounding box, these dimensions they come here. So yes,
so like now we have a box that's 64 units, and we want like 16 in, let's say, one direction. It would be 4 units per cell, like, or like between 2 nodes. And then, but then what is the delta x here is like the
not 2 units. We set here delta x as grid spacing. We say okay, between 2 nodes is one unit.
okay.
You will have obviously 4 blocks. Because you are discretizing the 64 with
Each block has
if you look again on this picture, yeah, so we define with block in X, we define these dimensions. Yeah, for example, in this case is 5. Yeah, then we have 5, 5, and then we have here 20. Okay, we say okay, our grid is 10, 20, 10. So it means then we have at the end here 4 blocks, 2 blocks in X direction, 4 blocks, and okay, that you need to have this in your head.
If bounding box has the same dimension as the block of X, then how many blocks do we have? If both have the same, if we set the block of X also.
Yeah, if we have here 64, 64.
So how many blocks do you think we have?
each block. Just like one block.
Yeah.
So then, this what I said. We can control with these 2 parameters how many blocks you want to have, and yeah, supposed to how big your block. Yeah, how big what you want to have, how big should be your block. So and you see, you can simply, if you have some, you want to debug something, you start with your simulation, but you don't sure with these blocks, you can easily convert your simulation to to grid node block without these blocks. You define the same dimensions in block, grid, and node, and block size, and you have standard grid, standard node grid. Yeah, so without this separation in blocks. So for example, it's very useful. It's very useful. For example, if you develop something new, some new approach, new boundary condition, or new kernel, and you are not sure if this arrow something happens through connection, through false exchange of data, or your algorithm. Yeah, then you can reduce this complicity. Yeah, you grid complicity to one block, and working with the standard or grid nodes, and only debug your algorithm, for example. Yeah, and look, okay, it's what's the problem.
I mean, when we talk about this at the moment, maybe it deserves to also say that the block is the smallest, the smallest parallelization
unit. Yes.
So when you have one block, you're running serial. So even if you do it on your laptop, and you know you have like 8 cores, then you should try to get a grid that has 8 blocks at least. Yeah?
I mean, there's something else. I mean, we have it's a little bit complicated. We could have multiple blocks in one process.
Yes, of course. But I mean, this is the smallest unit.
Smallest units, yes. Then, as of a better utilization, your hardware, but the typical, modern computers have more as a one core, and if you do some, simulation, then of course for better utilization, your hardware is using, a number of blocks related to number of cores in your computer. So that's which proportional, we can say. That's of course you will see. So, but at least the same number of blocks as you have as the cores you have. So, and okay. Yes, then this part, now we start with grid generation in principle. So first we need to define, okay, this, I call this grid cube. Martin means it's not a good name, but okay, we can grid bounding box, we can call it this grid.
Martin thinks it's not a good name because the cube has the same length.
Grid cuboid or grid bounding box. Actually, it means here we define a physical bounding box. What it means, you see this GB cuboid 3D. This is this primitives, what I told you about early, and we can find these primitives if we go to the basics folder, and here geometry 3D folder, and here are defined this all primitives. So, but the most of you use it are this cuboid, cylinder, and I think sphere, so line and so on. But it's a lot of primitives, and I use it in grid generation and set up your geometry and so on. And in this case, we use this cuboid to define this bounding box. Simple. And parameters, you can see this left button, left button corner, as in what is 3-dimensional, yeah, and then top right corner. So, and we define this bounding box, and then we can with this function, yeah, this you can see this also the static function. We can write out this geometry in some PowerView file. So this, yeah, very also useful, and I use this always to control, yeah, because this we don't have any GUI, yeah, and if you produce some primitives, maybe you have some error or something like this mistake, yeah, by defining this corners coordinates, because this is in your real coordinates, yeah, and typical. Okay, in our case it's very simple, yeah, but if you have some complex geometry and with real coordinates and real vertex units, and is not always obviously, yeah, this coordinates. And I use always, if I produce some geometry or I read some STL file, I use always to control this write geo object function to produce a VTK file, yeah, to later control in the ParaView. So, and here parameters are this grid cube is our this object, geo object, yeah. We need to apply here get function because it is, as you can see, this SPTR, this only alias load for shared pointer, yeah, correct. Is alias for shared pointer, as we are lazy a little bit, and you need always write std, yeah, this double point, so on, and we create this alias and use this. Okay, yeah, you can see now as IntelliSense had this line. So then we and in this case we have weak pointer, then no, as we use raw pointer, then we need access to this raw pointer. Okay, then apply this get thing. So then pass to yeah, for the file where we want to write this file, and here there's the last parameter we defined which writer, yeah, it's again I think it's template, no, that's not template, but we can choose this parameter depend of which file we want to write, yeah, which and there is defined different writers. We can look again in the basics. Writers here, yeah, writers, yeah, you can see different writers which we can use to in with this function actually, yeah, and we will write in different yeah, different formats, and if you don't find some format what you need, you can welcome implement new writer here, yeah, for your format what you need here. So and you can see it's a lot of, yeah, we have some, yeah, ABC and so on, tech plot, VTK, but a lot of VTK because we are working with ParaView. That's our main visualization software.
Okay, who is testing these things? Because I have not seen us using TechPlot for a long time.
Yeah, maybe I don't know it. Of course, any from these writers maybe don't work, but it is ASCII. I'm not sure. Yeah, maybe with not confirm with actual implementation of TechPlot and so on.
Okay.
But
Maybe
but
it's conform, we don't know.
yeah, we don't know because we don't use it. Yeah,
Yeah.
we don't use it. I touch a little bit this plot, TechPlot files as I was in this project with airfoil, because this aerodynamics guys use this CATIE and so on. Yeah, this software which TechPlot for visualization is as they say standard software. Yeah, but we don't use it. We use typically we use ParaView for our goals. And for ParaView we have yeah, different writers. As this, for example, this VTK binary and VTK ASCII, this so-called legacy VTK file, which was used early ParaView, but ParaView supports this file format also in the last versions. But maybe if you need this, you can use this. But typically we use this more modern, more new format is XML, which use XML as a base for this format. And you have different, also different, this is common XML file, ASCII, binary, and special this image XML image binary. This VTU, so-called VTU file. Yeah. And in this case, we use this common XML binary writer. Yeah, you can choose also binary or ASCII. I would say if you in your setup, developing your setup, typically I use ASCII, because if something wrong, yeah, you can always look inside this file and try to understand. As sometimes it's also helpful what is wrong, yeah. And in production time, of course, better is using binary, because it's less memory consumption and much more faster, yeah, for writing, for example, or reading. So, but you have this possibility to choose a file format. Okay, so in the same yeah, this refinement, as you can define this geometry for refinement, but we will speak about this in the second part, and then skip this at first. Then we define here our kernel. Yeah, this kernel object, and you can see again we use always this abstract class to define something. Yeah. As a type for kernel, but by creation we use, of course, concrete kernel. Yeah. In this case, K17, yeah, compressible nav stocks. So, and here we need also to create this so-called as a BC set object, and this object, yeah, this to control, to handle with the boundary condition nodes. Yeah, that's and I will say I don't want go now in details, but we need this. We need to create this and set in our kernel. Yeah, you can see function set actually we need this to is provide access kernel to the boundary conditions, nodes and so on, yes, and also control. Uh, we have also or we can difference between pre-collision boundary pre-collision boundary conditions and post-collision boundary conditions. Yeah, and this class or object also handles with this. Yeah, yeah, both. Yeah, but decided which in which moment should be call it and so on.
Yeah, but I mean, you, even though we probably don't want to go in detail on this, but because I stumbled over this too, why we have to do it when we have to do it anyway all the time. Maybe you say something that there's different options, and this is, I believe, related to whether you use the synth wall or the not synth wall.
Yeah. Okay. Yes. If you want to use a synth wall, then you want to you need to use, or you must to use a special BC set for this call. Yeah. We go back to the boundary conditions. BC set, but this BC set synth wall BC set is called. Then on this place, if you want to use this no slip synth wall boundary condition, you need to use this synth wall BC set. Yeah, this something specific for this. There's some implementation detail. Yeah, but
yes, I mean, we should potentially say that you could use synth walls all the time, but using synth walls is much more
expensive.
Much more expensive. So if you don't need them, which is almost always the time, you don't want to spend this money, so you go with the simple version, yeah, and spend this only when you really have this kind of problem.
Yeah. Yeah. Yeah, if you don't care, it will be works also. Yeah, with synth wall, but it's yeah, your simulation will be slower. Okay, so it's an important moment. And then in this line, yeah, we come. Okay, this line I will explain later. Also, I will. Simply briefly say, okay, we need this for domain decomposition, for load balancing, but I will talk about this in a second part. Restart part is again the second part. This restart and checkpointing, and okay, here new start. Okay, this is also related to this restarting, but in our case, what is interesting for us, this class, yeah, GenBlocks Grid Visitor. Now we see first visitor class, yeah, which we use. As I said, most of these visitors I use it in pre-processing. We are always in pre-processing, you see, yeah. So we create this object, yeah, the parameter grid cube or our bounding box. We give this visitor a bounding box object that he should know. He should know, yeah, how big is our simulation domain, and this object create, yeah, here we apply this except, yeah, this except typical standard function for these visitors. Yeah. You see, yeah, we apply this accept as a grid accept this visitor. Yeah, we say grid, okay, here is our visitor, here is implementation, something which we do something with grid, and grid object accept this implementation, and okay, the grid says, okay, do something. Yeah, you want to do something, I accept this. Yeah, it's means this.
The grid is ordered to accept it.
Yes, yeah, or ordered to accept this. Yeah, can we say? But what happens? This happens something with blocks actually. Yeah, or in this case, it was grid visitor. It happens then something with grid, and in this case, what happens? The visitor create blocks. Yeah, in this grid object, related to our bounding box. So we set a bounding box geometry in this visitor, and grid accepted this and accepted this visitor, and visitor create blocks then. After that, we have, because before we don't have any blocks in our grid. Yeah, before this step, it was only grid object with some parameters, but it's empty at first. Yeah. After that, we fill this with blocks. Yeah. After that, is fill it with blocks. Okay. Here some logs. Yeah, for parameters, it's only to control. And then, okay, I goes a little bit. Okay, we will, yeah, we will see later. This okay. Next step, we create geometry. Yeah, it was geometry for grid bounding box, and we fill this with blocks. Then we in this step we create a geometry for boundaries. Yeah, we need walls. We need walls. We need inflow. We need outflow, and that we have some cuboid domain, and we can also use this a cuboid object to create walls and boundaries and so on. Yeah, and in this step we create in y direction 2 walls in y direction, and in x direction inflow and outflow. Yeah, it's no boundary conditions, it's only geometry. Yeah, topological. It's topology for our boundary conditions. And we control this with with this right function. Yeah, we can then look in the purview. So, yes.
Question. Because I see like this, my ID equals 0 as repeated multiple times. And then I think you get it from get processor ID. And
Yes.
What
Yes.
is this 0? It's like the one that is master and the other
Uh,
one that is slave.
Typical, it's good question. It's very good question. This is we have, as I said, this we have MPI polarization, and we defined at the start here this communicator, and then you see communicator has this function get process ID. So we store in this variable, and it means the main concept, we can say we don't have master slave or something like this as decentralized. Each process works autonomous, we can say, and exchange information with nearest neighbor. So, and typical we have some root process which we use, for example, for output something, because if each process outputs something, yeah, then you can realize nothing on your screen, yeah. And typical, we choose one process which controls this output, for example, yeah, on the screen, and standard is a 0, yeah. But
you should potentially say that this is the output of the simple thing. So because it does not mean that when you write when the simulation runs, then it does the output through a master process.
yeah.
Each process writes their own file.
Yes, this is, yeah, I will explain this later. Yeah, that's only for your screen or is output file. If you start, for example, on cluster, yeah, you don't have a screen. Yeah, so you submit your drop in the queue, you don't see more. Yeah, you have this output file from the Slurm, for example, and then you can see this output. Yeah, and you don't want that each process, 12,000 process, yeah, put something in this file, you will see clear information. Then we choose one process for this. You say, okay, only this process, okay, in this case, only process 0, because, yeah, MPI, this each process does the same thing. Yeah, it's MPI is data parallelization. We parallelize not tasks, yeah, functionality, we parallelize data. We distribute data between more processes. In each process does the same. That's like in GPU. And we don't know that all processes told you that this is simultaneously something. Yeah, we say, okay, only process 0 say about what happens. Yeah, and you can achieve this if you say, okay, if this process 0, then make output. So on the screen or this output file, okay? And and you can, yes, this you can also say if this process 1, for example, it doesn't matter. Yeah, any one process.
Okay, obviously it is 0 because if you have only 1, then you always have 0.
Yes, then it's work. Yeah, then it's scalable. Yeah, it's because if you have only one process, because in background you have always MPI. Also, is if you don't start with MPI launcher, it's always MPI in the background. Yeah, and if you have some if, and you always have this ID. Yeah, and if you have only one process and this ID don't exist, yeah, so at least you have always ID 0. Yeah, then it works then for all cases. So okay, and then, yeah, you see each process do this, for example, some refine cube and so on, but only one process in this case write this geometry, because this geometry is the same on all processes, we can say. So, and but if you write your data, yeah, distributed data, then of course each process write each part of data, yeah, parallel. So okay, yeah, it was here. Okay, so that's topology for yeah, for our boundary conditions. So and here then, and then this, yeah, we can write this early, or call this early. In this case is later, because yeah, it doesn't matter in this case, but this is what we define here. Write block simulation observer. Yeah, now we see this observer thing. Yeah, and what typical observer does to simulation time. Yeah, and you can also write blocks. What does this visitor simple produce some output for your grid, block grid? Yeah, then you can control your block grid. There's only blocks. I can, in principle, I can illustrate this. Yeah, with oh, just a moment. I can illustrate this in far view. So, as we have this standard, the writers, typical you give writer or not writer, the simulation observer, the main path and main folder for your output. So root folder for your output. Yeah, in this case, you see this output laminar plane flow. Yeah, this passed to your output root, and then each simulation observer which produces some output files, yeah, create then subfolder structure. Yeah, for example, this or not always, or say something wrong. No, sorry. No, we define the self. Yeah, we define the self. Yeah, we define the self, but it's I use this, the subfolders structure to separate. Yeah, different. Okay, actually, is the thing for the user. Yeah, how you organize your output in principle. Yeah, this you're totally flexible. You can, of course, everything write in the same folder, but it is of course different to recognize them later. And I create always some subvolta structure. Yeah, you can see, for example, here that there where I use this subfolder geo through some geometry files, and then later for other let me say.
Also,
Yes.
a quick question. The idea behind being able to, or that you specify like this kind of phases and then assign boundary conditions, is that because then you are more flexible in assigning boundary conditions compared to the GPU code, or is that just something that just grew over time? Because now you're still trying to set the phases of this cuboid, right? But I mean, is the idea that you basically can have more complex shapes or something like that?
The idea as that we have these iterators. Yeah, we will see later. Yeah, we use iterators, this object, which uses geometry object to find boundary nodes. Yeah, and set this boundary information on these nodes. So
you have to specify where your boundaries are supposed to be. The only ones that you can adjust intrinsically are periodic boundaries, where that's the only one that you get through the bounding box.
But in the GPU, you could also just say that you take the far east, the far west, and then you just set those conditions, right? So my question is basically, why choose this formulation compared to the GPU formulation for setting the boundary?
This functionality was this more flexible, of course. This interactors functionality and with boundary condition nodes, it was always early implemented in VirtualFluids. I just use this implementation later and extend with the strategies, pattern and different strategies.
So
But
you're not in general assuming that the pressure boundary condition needs to be on one end of the domain.
Yeah, exactly. That's what I mean. So you can
Yes,
basically.
you always, for each boundary condition other than periodic boundary condition, you have to specify, you have to generate an object to tell the grid generator where this thing actually is.
Yeah.
Yeah, and I also add something, maybe you faced several classes dealing with BC, you have BC and you have BC strategy and you have algorithm. I mean, if you show the table, Constantine, it's like we separate physics from algorithms. Like, yeah, the table for boundary. Exactly. So, physically you would have pressure, no sled, and etc. But then, how this is realized? I mean, to achieve, for example, the pressure, there are several algorithms, we call them strategies to achieve this. You may develop your own way to predefine a no-slip BC, for example. So this is how it's done. So you might have like more than class in order to.
So the reason, I mean, one reason for this separation is that the boundary conditions. So boundary conditions may require some data or some data structure. So they're not just setting a value necessarily, right? But they need, for example, if you have an extrapolation outflow, then obviously you need something. You need to know something of what is inside.
Yeah.
And so the different boundary conditions, they have different requirements on their data structure already, even before we go to the algorithm. So we can actually, correct me if I'm wrong, yeah, but we can group them according to what they need. And Konstantin just said this, that there are boundary conditions that are pre-collision and post-collision. So this is then also important where they are applied in the cycle. Yeah. So yes, but this is.
Yeah.
Saying this correctly, right?
Yeah, it's correctly. Yeah, it's it's more flexible construction. Yeah, it's because I think you can define this not especially cuboid for you can take any geometry in principle for your boundary condition.
So
Yeah.
the typical example for for a velocity boundary condition could be a turning wheel. Yeah. That is obviously different from.
It's not always, for example, channel with some object in the middle. Yeah, think about inverse. Yeah, you have the pipe in this pipe, something heavy or some not so straight pipe. Yeah, some pipe which or blood vessel. Yeah, something like this. So. Okay, it's not simple. Say, okay, right is this boundary condition, left and this. Yeah, this.
Oh yeah, exactly. That's why I was.
Yeah,
asking as
yeah.
well. So that's the idea behind it. Okay.
Yeah, it's of course for simple cases maybe simple to say simple direction here. It flows in this direction. That's it. But it's not more. I think our approach is more general. Yeah.
Yeah.
Okay. So may I continue? Yeah. Okay. About this right block simulation, I want to show you. Yeah. So as I said, the typical simulation observers, and we can see here as a parameter use only, you see this path name, yeah, this root of your output folder, okay? And in this case, write object, in this case, this is not the simulation observer, yeah, and it's, in principle this write is write as legacy code was, and in this case you see it's simple direct path ways file written, okay. But I want to consider this structure, yeah, as a simulation observer. As I said, actually you use some predefined subfolder structure. For example, the write block simulation observer, we can look here, yeah, create these blocks subfolder and writes in this subfolder information about blocks, block grid, yeah. The macroscopic quantity simulation observer create MQ subfolder and so on. Yeah, this predefined subfolder structure to better separation of the output files. But in the case of some inconsistency, but yeah, it's also not the part of the simulation observer classes. In this case, we have some this write object, yeah, a function, but to get this consistency is the subfolder. I also recommend use also here this subfolder structure, okay, and I create some subfolder geo and write this geo files, yeah, in geo subfolder, yeah. But if you use simulation observer provides this subfolder structure. So, and we can look, yeah, in geo what here what we before generated and write it. Yeah, if you start, you will have this also, but I want simply to show you. Yeah, we have this two walls, yeah, then inflow outflow, so, and the grid cube, yeah, this bounding box what we created. Okay, we need to XML, choose this XML unstructured grid. So and then I say can I do this? Okay, I cannot do this. So if I choose frame for our boundary, so you can see, yeah, this is our simulation domain. Yeah, this is this grid box, the simulation domain with geometry for boundary conditions. Yeah, this for boundary. In this z direction we don't need, because we set it this for periodic. So, but so can you control, yeah, immediately control in the paraview you what you generated then. So, and okay, and this write block simulation observer write actually in this subfolder blocks, and write in also in parallel file is pvd, but in this case we yeah, we have only one process, then it's only one file, you see, yeah. Okay, but
you open the group.
Yeah,
this is something, so because they write out multiple files, there's always this
Genau, is something different to the GPU code. If you also yesterday tried to open something, produce it with GPU code, the GPU code write this parallel files in the parallel file, but only each file without this group file, and in CPU we have this PVD as parallel this I think call it parallel VTK data set on something like this. As you see, collection, blocks collection. This is collection file. This is a simple, you have also seen. Okay, okay, nice. So okay, sorry, I was. Okay, sorry. I was not so concentrated. Okay, then forget. Everything okay.
It was his invention.
Okay, everything okay. Then okay. We open this PVD. It's okay.
Then we get an error.
Always try to be as good as possible.
I mean, if you open the other one, it will open.
Okay, that's something. But we need to start. What? That's something wrong with this file, I think. And let's start. Let's start. some problems. Okay, but we will see. I can show you the PVD is a simple ASCII file with the text, and we can control here which files in there's only one process VTU, but okay, this is binary, it's in right and binary. But I think this the problem we don't run in before. Okay, we tried and run this and if it's control after that. Okay, I will not struggle it with ParaView. We continue with next step. Do you have any questions? Lunch. Okay. Yes. Okay. Then we can make
Where's a logical break that you have?
a logical break. We very very far from logical break actually. We make break now and continue then after lunch.
You have already broken it.
Yeah.
Yes.
That's
Okay.
very